Today we're looking at area between curves. So far the areas we've found is, say that we've got a curve, we would find the area of the function bound by the x-axis, could be the y-axis as well, but that's generally what we've been doing. So today we'll do something like this, where we've got two curves and we want the area between the two curves. Alright, how's it done? Well, you could do it intuitively. So here's our first function here, f of x, and here's our second function here, g of x. And what we want to do is find this area in between. Well, here's a strategy. Let's get the area under the curve f of x. So that's it there. That would be all of that. Then what we would do is get the area under g of x, which would be that. And then what I would do is remove the area under g of x from f of x. And that is what's going on with this line in your notes there. Okay, so they're getting the area under the curve for f of x between b and a, and the area under the curve for g of x between b and a, and removing the result. Now, note that we can actually write that like this, which is the kind of reverse process of splitting the integral. So when I split the integral, it would become this, or I could recombine it into one whole integral. Now, why would I do that and not do it separately? Well, often you can get g of x removed from f of x, and it simplifies down to an easier function to integrate. So invariably that happens. So to find the area between two curves, f of x and g of x, what you want to do is find the points of intersection. I'll explain why in a sec. These x coordinates will be the terminals for the definite integral. Set up the integral with top curve, take away bottom curve with terminals. Okay, so top curve, take away bottom curve. You need to have a graph to know which one's the top and which one's the bottom, i.e., sketch it. If the curves change, which is the top and the bottom, break the integral with the appropriate terminal values. And finally, and this is a really important point, doesn't matter if the graph is below or above the x-axis. It doesn't matter where it is on the Cartesian plane. It can calculate this. Okay. Now, why is that? Well, it's interesting. All right. So if this is our top function here, okay, and so let's call this f of x. Let's call this bottom function here g of x between these 2 points here. What will happen is that my top function is going to have a negative area, so negative small, and what will happen is my bottom function will have a negative area, which is negative larger. Right, and when I subtract, so I'm going to go negative small, take away negative larger. Okay, and what happens is you get negative small plus larger. Okay, and in essence, because that's negative, it'll be trumped by the positive there, and you'll get your positive area. Okay, so the signs actually just take care of themselves. It's quite elegant the way it all works out. Okay, so find the area between the two curves. So this blue curve is, what is it, G, red curve is F. All right, so let's do this first one here. So I'm going to integrate, so our area equals between C1 and A, top function is f of x, bottom function is g of x. Okay, so notice that the intersections form the terminals. Okay, now we're going to add to that integral C2, C1, top function is g of x, bottom function is not h of x, it's f of x. Plus, over here, top function is f of x, bottom function is g of x. Now, can you please make sure you put the dx here that I've forgotten to do so far? All right, and then the final one is this one here. So I'm going to be a bit rebellious here. I know I said top function take away bottom function, but I'm going to do bottom function take away top function. Now, what's going to happen? Well, if you can understand what's going to happen, we're going to go bottom function, which is small area, remove large area. So what we're going to get is this area here, albeit it's the negative version of it. Okay, so if I get the negative version of it, why don't I just stick a negative sign out here, and it will negate the negative. Okay, B and C3. So what we could do is that we could also add it and reverse the terminals, or we could just do add g of x take away f of x. So this one here is just me experimenting around. Why experiment with something that works? Well, VCART did it a few years ago and wrote a corker of a question that students found tricky, where they did things like this. All right, so let's try it out for real. All right, find the area of the region bounded by the graphs f of x equals x cubed and g of x equals x. So this one here is g of x, this blue one here is f of x. All right, so what I can do here is I can see that this area here and this area here is exactly the same, the symmetry here. So when I integrate, I'm going to go area equals to integral. All right, now what I need to do is work out, it's going to be between 0 and up to what I believe is 1. Let's confirm it. I'm going to find out the intersection point between the functions. So it's x cubed equals x cubed take x equals 0, x squared take 1 equals 0, x equals 0, x equals plus or minus 1. All right, so yeah, it is indeed 1. And we presume 1. Okay, so I'm going to go 1. Now, what's my top function? It's g of x. Take away bottom function is f of x dx. All right, let's do it. Not quite ready for that yet. Okay, g of x, x take x cubed. Well, let's bang one in. Bang 0 in. Quarter removed from a half is a quarter. All right, so half a unit squared. All right, see how the calculator went with that one or goes with that one. 1, 0, x take x cubed dx. Okay, it's a quarter and multiply it by 2 and it's a half. All right. Find the area of the shaded region of the graph. Okay, so what we want to do is find out these intersection points here. So we're going to go and say that the intersection occurs when cosine x is the same as sine x. Now, how are we going to solve that? I'm going to use this property here. I'm going to divide both sides by cosine x, and 1 equals tan x. And the intersection, or when is tan 1, it's going to happen on a 45-degree angle and down here at 5 pi on 4. So x is equal to pi on 4 and 5 pi on 4. All right, so that's important now because that gives us the terminals for our integral. Okay, so area equals 5 pi on 4 and pi on 4. Now, our function or our top function is the blue, which is sine x. Take away cosine x dx. All right, now sine x becomes negative cosine x, and cosine x will stay negative sine x between 5 pi on 4 and pi on 4. All right, so pop in our values. Negative cosine 5 pi on 4, take away sine of 5 pi on 4, take away negative cosine pi on 4, take away cosine, sine. Pi on 4. Okay, area equals. Okay, so cosine of 5 pi on 4 is down here. So that's going to be negative 1 on root 2. And because it's negative 1 on root 2, that's going to be 1 on root 2 because that negates the negative. This is also going to be negative, which this will negate the negative, 1 on root 2. Takeaway. This one here is going to be positive and positive. So that's going to be negative 1 on root 2. Take away 1 on root 2. Oops. Okay, so this one here is going to be 2 over root 2, subtract negative. So this is going to be take negative 2 over root 2, which will add it, which is area equals 4 over root 2 units squared. Okay, let's try it out. Then and it was sine x, take away cosine x. 2 root 2, what have they done? Area equals 4 times root 2 over 2, 1, 2. So yeah, the calc has rationalised the denominator, which is good. All right, this is a tricky one. Okay, so parts of the graphs of the functions, so we've got f, this function here, g, this function here, are shown in the diagram. The graphs intersect when x is equal to 0 and x is equal to m. That's what we have to do. The area of the shaded region is 64. Find the value of a and the value of m. All right. So what I presume we're going to do is 64 equals integral between m and 0. Top function is g of x, and g of x is ax. Subtract bottom function is f of x. X to the 3, take ax dx. All right, let's see what happens here. 64 equals between m and 0, ax take x cubed plus ax dx. 64 m 0, 2ax take away x cubed dx. 64 equals up by 1, which is 2, divide by 2, ax squared. Up by 1 is 4 over 4 between m and 0. 64 equals, let's pop m in, am squared, take away m to the 4 on 4. So that is that one, and 0 goes in and we'll make it 0 going to be anything? No, it's not. So I can just leave it as that. Okay, so obviously we've got a and an m and an m. We've got two unknowns, which means that we need to form a second equation. So this says to me that this is going to be a simultaneous equations problem. Now, what else do I know? That I know that g of x is the same as f of x at the point x equals m. So what I'm going to do is actually let the two functions equal each other. So I'm going to say that ax equals x to the 3 take ax. Okay, so I've just said that is the same as that. And when does this occur? It occurs when x is equal to m. So let's go and write that as am equals m to the 3 take am. All right, now we'll go 2am equals m to the 3, divide by m, got 2a equals m squared. And what I'm going to do is I'm going to let a be the subject. A is equal to m squared on 2. Now that I've got that, I'm going to pop it into this equation here to get it down to one variable. So I'm going to get 64 equals m squared over 2 times m squared over m squared over 4. Okay, that's going to be 64 equals m to the 4 over 2. Have I made a little mistake here? I have. When I popped in m here, that should be m to the 4. And that should be m to the 4. Okay, take away m to the 4 over 4. Alright, now 64 equals, let's get a common denominator, times 2 times 2. So that's 2m to the 4, take away m to the 4 over 4. And that's going to be 64 equals 2, just m to the 4. Now we're going to do 64 times 4. Oof. 6, 1, 6 4s are 24, 25, 256. Alright, so now we're going to fourth root both sides. And staggeringly, when I fourth root both sides, that's going to start me off with 4. Okay, so 4 times 4 times 4 times 4, or 4 to the 4, is equal to 256. Okay, so m equals 4. There's our first value, excuse me. Now what I can do is sub that into there. So I'm going to get a equals 4 squared, which is 16 on 2. A equals 8. There's our values there.